Welcome back. When we finished our discussion last time, we were discussing sampling and the sampling theorem and implications and applications of that. And we found that sampling, we could sample a continuous time signal into a list of numbers, x of n, and perfectly reconstruct that continuous time signal, at least theoretically. And this is really remarkable because, as you've probably recall from calculus, between any 2 points in a continuous signal, you have an infinite number of points. And now we have this uncountable infinity mapping to a countable infinity number of points indexed by n, here x of n. But this only works because we know x of t is band limited. So with that extra constraint, we know that we can take some continuous signal and we can turn it into a list of numbers that we can then analyze and operate on. So there are other ways that we can take a continuous signal and come up with a list of numbers. One of them, right here, you may be familiar with. We have here an interval from 0 to 1, and in this first block here we have a continuous signal represented by this polynomial. Well, we can represent this particular one, this polynomial signal, with a list of four numbers. We have the coefficients for each of the powers of t. And that's really what a polynomial is, right? Is that we can represent it by just the coefficients. Now, here we're just dealing with t up to the power of 3, but you're probably familiar with another function going from 0 to infinity, so we could go to infinite order here. And if we take our coefficients to be the kth derivatives evaluated at 0 all over k factorial, we come up with the Taylor or Maclaurin series. So we can use other examples. This isn't the only one. For example, we could use x of t is equal to a sum over k from 0 of alpha k for different alpha, pk of t, and this could be, say, Lagrange polynomials, or B-splines. So once again, just a few ways that we can take a continuous time signal that has some limitations. You can't take an arbitrary continuous signal and turn it into a list of numbers because you have an uncountably infinite number of degrees of freedom. But once you put some constraints on it, and in this case the constraint we put on it was that we're just looking at an interval from 0 to 1, and we have a differentiable signal, then everything is fine. And so we'll find that there are many cases where this works out. So in general, you can now there are more examples. Look at the course notes on Canvas. There's also a link to a website managed by Dr. Davenport that has these same notes on it, that's linked from our Canvas page. But there are more examples on that. So, why do we care? You might guess right away. The reason we did sampling of continuous time signals in the regular DSP sense was because we wanted something that we could represent on a computer. More generally, our goal is to represent continuous signals in a discrete way so we can do processing. To enable the use of linear algebra. So go ahead and take a look at the notes for some more examples, but that's the main purpose of sampling, or many other things that we could do. Wavelets, for example, are another way of going from a continuous signal to a discrete list of numbers that we can operate on. Splines, Lagrange polynomials, other polynomial approximations are commonly used. Even so, sampling is the most commonly used, and we're going to often disregard traditional sampling in the DSP sense. But I want you to know that this generalizes, and that's one of the beauties of using linear algebra. Well, from this point on, the course becomes very linear algebra heavy. So in our next lecture, we're going to talk about vector spaces.